Hi everyone! Last week we talked about electrophilic aromatic substitution reactions, and that involved adding a functional group to a benzene ring. This week we're going to cover the second half of that same chapter, and we're going to categorize different functional groups as activators and deactivators, and that's going to have an effect on how a second group would add to the benzene ring. So as an example, let's say we already added a methyl group to the benzene ring, and now we want to add a second group. So let's say we want to add a nitrate group, NO2. Which reagents would we use to add a nitrate group? Nitric acid followed by sulfuric acid. All right, now, where would the nitrate group add? It's okay if you don't know, because there are three possibilities. We could see the nitro group add to the ortho position, so right next to the methyl group. And let's just highlight that position, and we'll color code it. Or the nitrate group could add to the meta position, or it could add to the para position, which is right across from that methyl group. All right, so we've got our three different possibilities here. So if we actually run this experiment in a lab, what we find is that 63% of our product is made up of the ortho product, 3% is the meta product, and then the last 34% is the para product. So what this tells us is that we actually have a mixture of products in our final solution, and we're mostly producing ortho and para products. Now, why is that? Well, that methyl group, also called an alkyl group, is also called an activating group or an electron donating group. So how is that methyl group donating electrons to the ring? Well, it's not physically donating electrons, but it is donating some electron density through hyperconjugation. So remember, a long time ago we talked about carbocations and how they're stabilized through hyperconjugation with other alkyl groups. And it's really the orbitals that overlap and stabilize that positive charge. So a tertiary carbocation would be more stable than a primary carbocation, for instance. But if you do want to go back and review hyperconjugation, I definitely recommend doing that. It's a really good concept to know. All right, so because alkyl groups are electron donating groups, they are going to activate the benzene ring. So electron donating groups activate the ring. Now, if the ring is activated by one of these electron donating groups, that means that a second group would add to either the ortho or the para position. So we say that electron donating groups, or EDG, are ortho-para directors. Okay, why? Why are they ortho-para directors? Well, let's look at the intermediate for this type of reaction. So again, let's say we're starting with toluene. So we have a methyl group on our benzene ring. And we're going to add that nitro group that we talked about. Oh, and actually, let me draw my double bonds in slightly different places here, just so it's easier to see the reaction. So remember, in an electrophilic aromatic substitution reaction, one of the double bonds is going to give up its pi electrons to form a new sigma bond. In this case with NO2. And here we're looking at the ortho addition of NO2. So what we end up forming is that sigma complex intermediate, also known as the rhenium ion. And because we moved those pi electrons over to form that new bond with NO2, that leaves a positive charge on the other carbon that's right next to the CH3 group, the methyl group. Now this is really, this is a very stable carbocation because that methyl group is electron donating. So it is donating some electron density to that positive charge, which again creates a more stable carbocation through hyperconjugation. So let's just make a little note. The CH3 group stabilizes the positive charge. Now, we could draw our resonance structures here as well. So the positive charge isn't going to just stay in that one spot. It's actually distributed around the ring. And we end up with partial positive charges around the ring. So that is also stabilizing. Okay, now let's look at the situation where we add that NO2 group to the meta position, because we already saw that we don't produce very much of that meta product, but let's see why we don't produce very much of the meta product. So again, we're performing that electrophilic aromatic substitution reaction. So pi electrons are going to form a new bond with NO2. And we end up with our sigma complex. Okay, so notice that the positive charge is not near that methyl group, that electron donating group. So the methyl group is not stabilizing that positive charge where it is right now. Let's draw our resonance structures and just see if that changes anything. Let's see if we can move it closer. So we'll move some pi electrons over. All right, so looking at this resonance structure, the positive charge still isn't as close to the methyl group as it is when we add NO2 to the ortho position. Now let's draw our last resonance structure just to make sure. All right, and again, that positive charge is just not as close to the methyl group as it is up above. And this is partly why we don't form any of the meta product, or we form very, very, very small amounts of the meta product when we have an electron donating group. So again, if you have an electron donating group present on the ring, the meta product when you add NO2 is actually unstable compared to ortho and para. So let's look at the para reaction. Oh, my pen always goes bold towards the bottom of the screen. I don't know why. All right, so we're adding our NO2 group to the para position. And we're forming our intermediate. Okay, so the way we've drawn this here, the positive charge is nowhere near that methyl group again. But let's draw our resonance structures just to see if we can get it any closer. So we'll move our pi electrons over. All right, so in this resonance structure, we can clearly see that the positive charge is right next to that methyl group. So now the methyl group is stabilizing that positive charge through hyperconjugation. So again, this is why we end up with ortho products and para products and very, very, very small amounts of meta, or none at all for meta. All right, let's draw our last resonance structure just to be thorough here. All right, and remember with these resonance structures, we actually have a hybrid structure where we have partial positive charges around the ring. Now let's go back a slide, and I want to ask you, why do we have twice as much ortho as para? So why did we form 63% of the ortho product and only 34% of the para product? So how many ortho positions are there on the ring? 2, right? We could have also added NO2 to the left here. But how many para positions do we have? Only 1. So there's a 2-to-1 ratio between ortho and para positions. So that means we're going to produce twice as much ortho product compared to the para product. So just something to remember and keep in mind there. All right, so again, electron donating groups are ortho-para directors, and that is because looking at the intermediates, the sigma complex for the ortho and para reactions are more stable. All right, and I'm just going to add one last note down at the bottom here that the CH3 group again stabilizes that positive charge. Okay, so let's talk about different types of activating groups or electron donating groups. Now, there are three categories for electron donating groups. We can have strong activators, moderate activators, and weak activators. So let's start with the strong activators. And again, these can also be called electron donating groups. All right, so the first example is phenol. So that's a benzene ring with an OH group attached. The next one has a negatively charged oxygen. And then we can also just have different types of amines bonded to the benzene ring. So we could have a primary amine, a secondary amine, where we have some other alkyl group bonded to that nitrogen. And finally, a tertiary amine, where we have two other alkyl groups bonded to that nitrogen. So notice that the one thing all of these have in common, they all have a lone pair that they can create a resonance structure with. And in that resonance structure, we're actually going to move electrons into the ring. So let's write that down. As an example, let's look at our alcohol group. So again, we could show one of those lone pairs coming down to form a double bond, and then one of our pi sets of pi electrons can move over. And then we could keep moving that set of electrons around the ring. So we can move that down, move the next set over. All right, and we can go again. Just keep moving those pi electrons around. Oops, I hit the next slide. And finally, if we move our electrons down in this step, we can move electrons back up to oxygen, and that's just going to give us our original molecule there. So as you can see, we're adding electrons into the ring, and we're activating that ring. So this is going to create our nucleophile that can then grab onto some other group. Okay, so this becomes more nucleophilic. All right. Now, notice the placement of the electron or lone pairs. So at first we had one at the ortho position. Then we moved electrons around, and then the lone pair was on the para position. And finally, it ended up back on the ortho position, but on the other side of the ring. And this is why electron donating groups are ortho-para directors, because we create nucleophilic spots at the ortho and para positions. Now let's look at some moderate activators. So these are not quite as strong. So moderate activators would be, for instance, an ether. We could have an ester. Or an amide. Oh, I forgot a hydrogen on the amide. There we go. Okay, so why are these moderate activators? So the ether just isn't quite as strong of an activator as some of the other examples we saw on the last slide. But if we look at the ester and the amide, there's some competing resonance going on. So if we look at the ester, for instance, we could move electrons to the right or to the left. So electrons could go towards the ring or away from the ring. And it's the same for the amide. That lone pair of electrons could move to the right or to the left. So there's competing resonance structures there. So these are still relatively good activators, but they're just not as strong as the ones that we saw earlier. And then finally, we have our weak activators. And this would pretty much be anything with an alkyl group attached. So toluene is actually a weak activator. You could have an ethyl group, or maybe a tert-butyl group, just any sort of alkyl group, really. So again, these are weakly activating because they're donating electron density through hyperconjugation instead of through a resonance structure. These alkyl groups are still activators, they're just not quite as strong. Now let's also think about the kinetics of these different activators. So how would the strength of an electron donating group affect the rate of a reaction? So let's look at our strong activators. Do you think that these will cause faster reactions or slower reactions? Faster reactions. So let's just make a note that these are fast reactions. So that would be if you're adding a second group onto the ring. If you have a really strong activator already present on the ring, that second group is going to add really quickly to an ortho or para position. However, if you have a moderate activator, then the speed of the reaction is going to be moderate. Actually, I'll write this in a different color since I already wrote something next to that. And our weak activators, those are somewhat fast reactions. They're not prohibitively slow, so they're not going to prevent a reaction from occurring. So we'll just say somewhat fast. But they are slower compared to if you had a moderate or strong activator. All right, and then your textbook also kind of walks through more of the kinetics and thermodynamics of each of these different types of reactions that we talked about. But next time, we're going to talk about deactivators. So those are groups that are electron withdrawing. So they draw electrons away from the ring. So I will see you in that video.